Hello everyone, welcome to this lecture on solver math and settings. This lecture is part of the CFD modeling using CFX course by Learn CX, and in this particular lecture we will study some of the inputs related to solver settings and what is the mathematics behind the same. So let us begin our lecture now. What we have is the first slide where we define the finite volume method. Within the finite volume method, any physical phenomenon is governed by some conservation laws, that is given by partial differential equations, and any CFD solver solves flow using the Navier-Stokes equations, and these are numerical equations represent the solution for the visualization, which we after solution is obtained, which we post-processor see using various techniques. So finite volume method, also known as control volume method, is basically a numerical discretization method for solving partial differential equations. All the discretization method finally convert the non-linear partial differential equations into algebraic equations, and the ones that are used in CFX also do the same. So the formed set of a linear algebraic equation is then solved iteratively, and the coefficients been updated every iterations, which is sort of a matrix solution technique which is followed. So this is the overview of any finite volume method algorithm that is the same even in CFX. So within the finite volume method, the strategy is first to have a partial differential equation, a set of partial differential equation which describes the physical phenomenon. In this case it is Navier-Stokes equations. Then we volume integral then we volume integrate these partial differential equations to obtain their integral forms. After that we use the Gauss divergence theorems, and the volume plus surface integral form of PDEs is obtained, and then we basically use them on the discretized geometry, where we have the discretized form in which we convert the surface integral into phase summations. So this is the step where the integral equations gets converted into algebraic equations by using phase summation, and the phase approximation techniques further convert them into linear algebraic equations using upwinding schemes. This is the overview of the finite volume process. So an example here is, let's say we have a differential equation for a variable called phi, and in which we have convection equal to diffusion plus source. This is the sort of the partial differential equation where we are using a transport equation for the variable phi. Then we have the finite volume integration for the same. After integrating this equation, we have this particular equation which is in integral form. Then we have the finite volume discretized equation where we use summation to define integrals, and then finally we have the linear algebraic equations, which is used based on different algebraic techniques on each cell. So this is the example for a general transport equation for quantity phi or a variable phi.